We have now come to logic gates, and any discussion about logic gates begins with the inverter, or the NOT gate. The NOT gate performs a circuit function called inversion or complementation. If you have seen the video on one's complement, this may be somewhat familiar to you already. The NOT gate inverts whatever signal goes into it. In other words, the complement of the input signal is found on the output. A 0 becomes a 1, and a 1 becomes a 0. The picture you've been looking at are the common symbols for the inverter. The input is on the left and the output is on the right. The little bubble is the negation indicator. This tells us where the inversion occurs. When the bubble is on the output, the inverter is referred to as an active low output because the output is in an asserted low state. When the bubble is on the input, the inverter is referred to as an active low input because the input has an asserted state of low. If there is no bubble, a 1 is the active asserted state, and so the input or output is called active high. Okay, so what is an asserted state? That means when the circuit is active, what is being applied to the input or the output without some other signal being applied. If the inverter has no voltage on the output until something happens to the inverter, then the output has an asserted low state, and the bubble is on the output. This is nearly always the case, and so we will see this symbol used the most. Before we go any further, there are two more concepts that need to be covered. The first is truth tables. A truth table is a table of inputs and outputs. Inputs are usually given letters of the alphabet that are near the beginning, and outputs are given letters near the end of the alphabet. Then the table is filled out with every combination of inputs that the logic circuit can have, and what the output or outputs would be. To make sure that we have every combination of inputs, we simply count up in binary from 0 to all ones. Every logic gate has its own unique truth table. Later, we're going to combine these gates into more complicated circuits and make truth tables for them that resemble this table here. The second concept that we need to cover is timing diagrams. Now, we briefly discussed these back in the first section videos. As a refresher, a timing diagram is a graph that shows the relationships of all the waveforms associated with a circuit at any point in time. Here's a timing diagram for some circuit. Notice that you read it from left to right. Now, I used to confuse myself with these diagrams because I would imagine the signal being fed into the circuit, starting with the right-hand side and then moving into the circuit from right to left. So don't do that. The first signal is on the left and generally starts with t equals 0. We'll use the timing diagrams to show the operation of our gates. Later in this series, the timing diagrams will be essential for showing the operation of other circuit elements and more complicated circuits. So now that we have a handle on truth tables and timing diagrams, let's go back to our inverter. Now, as I said before, the NOT gate inverts the input signal. A 1 becomes a 0, and a 0 becomes a 1. Let's make a truth table of this operation. We'll call the input A, and the output we'll call X. Under the input, we count in binary, 0 and 1. Now we go to the output column. If the input is 0, then the output is 1, so we put a 1 in the X column. Next, if the input is 1, then the output is 0, so we put a 0 in the X column. And there we have the truth table for the NOT gate. We can also make a timing diagram for the inverter. The top waveform will be the input. The bottom waveform will be the output. All we need is two times on our diagram, one where the input goes from low to high, and one where the input goes from high to low. Let's draw our input just like that. It starts low, and then at t equals 0, it goes high. Then, at t equals 1, it drops to low. Now we make the output waveform. Where the input is low, the output is high, so our waveform starts high. Then at t equals 0, when the input becomes high, our output drops to low. At t equals 1, our input drops to low, so our output rises to high. This is the full timing diagram of the NOT gate. It's pretty much analogous to our truth table. T equals 0 is the second row of our truth table. Input is 1 and output is 0. T equals 1 is the first row. Input is 0 and output is 1. Perhaps this symbol looked familiar when you first saw it at the beginning of this video. And that's because we used it in the video for ones complement. An application of the inverter is producing the ones complement of a binary input. We can find the ones complement of an 8-bit binary number using 8 inverters in parallel. Whatever 8-bit binary signal is input, the output will be the ones complement, just like we're seeing here. The last thing we can talk about as far as the inverter is concerned is the Boolean expression for inversion. Boolean algebra will be covered extensively in section 4, but it's worth going over now. We represent negation using a bar over the input variable. Our variable here was a, and the output is x, so the Boolean expression for the NOT gate is this. The bar over the a tells us that x is the complement of a. When a is 0, x is 1, and when a is 1, x is 0. That's pretty much it for the NOT gate. Next, we're going to take a look at the AND gate. Until next time.